Hey, MYP Physics. This is the second part of our electrostatics introduction videos. Okay, and today we're going to talk about Coulomb's law and measuring electrostatic forces. So for the objectives today, the first thing we're going to do is understand what are the units of charge, what are coulombs, and what does it mean in terms of the particles that make charge. Okay, then we're going to talk about calculating electrostatic forces between charges. And the last little bit is we're going to talk about practical applications of electrostatic forces. Okay, so first of all, when you see a problem or you read your physics classroom pages and they talk about charge and they say that something is charged with -1 coulombs. Well, what exactly does that mean? All right, so in the last little talk that I gave you guys, we talked about charge-carrying particles, electrons and protons. Okay, those are the particles that carry charge. Now, before we knew about electrons and protons, we still knew about charge, and we named it, and we measured the forces of charge, but we didn't know that electrons and protons caused it. Okay, but now we do. And then next year when we do atomic physics, you'll learn more about how we discovered the actual charge of electrons and protons. But we said that an electron has a charge of -1.6 times 10 to the minus 19 coulombs. That's the point today. What is a coulomb? Okay, that's the unit of charge. And a proton is just the opposite. It has +1.6 times 10 to the negative 19 coulombs. Okay, so if a question said, if I charged up an object with -1 coulombs, how many electrons are inside -1 coulombs? So I'd be able to calculate the number of electrons is equal to -1 coulombs divided by -1.6 times 10 to the negative 19 coulombs per electron. And that would give me the total number of electrons. That's probably a very large number. That's going to be 6.24 times 10 to the 18 electrons. I don't even know what name that would be. What would be times 10 to the 18? I know times 10 to the 9 is a billion. So it's like a billion electrons in there. So when anything is charged up with a coulomb of charge, it has a lot of electrons. And your electricity that's running through the wall is carrying at least a coulomb of charge per second. That's how many electrons are flying past you in a second if you have 1 ampere of current. Okay, so that's why it's dangerous to be working with that kind of current. That's a lot of electrons flying through you in one point of time. Okay, now if I had a +1 coulomb, okay, and then it's the same. I would have 6.2 times 10 to the 24 protons in excess in that material. Okay, so that's the nature of charge. All right, so we can all agree that a coulomb is a heck of a lot of electrons, and most charged objects are probably not carrying a coulomb of charge. They're probably carrying much less than that. So when you read problems in your book, you're going to see that the charges they're talking about are not times 10 to the 1 or anything like that coulombs. They're more like very, very small, like micro coulombs or nano coulombs, because that's more realistic, okay? Right, but when we have something like that, that's a lot of charge stored in a certain amount of place, okay? So to summarize, charges are formed by having electrons and protons on a material, okay? I can calculate the total number of charge by, if I knew exactly how many electrons I had and I multiplied by the charge of each electron, that would tell me the charge that each material has, okay? So what next, okay? After that, let's talk about something that I tried to present, which is the concept of conservation of charge, okay? So if I have a charged object, and this charged object, let's say, has +2 coulombs of charge. Now, again, that's a lot of charge that charged glass would have, okay? And if I approach a pith ball that's neutral, okay, and I touch that pith ball, what's going to happen is all that charge is going to want to even out, okay? All this charge on that glass rod is repelling. It doesn't want to be next to each other, okay? So once that charged rod touches the pith ball, okay, the electrons in the pith ball are going to move to that rod, and the result is going to be the rod is going to have +1 coulombs, and the pith ball is going to have +1 coulombs. So what's happening is there's a driving force to even out that charge, okay? And that driving force is repulsion. It wants to spread that charge out as much as possible, okay? And that's the idea of conservation of charge. Conservation of charge states that the total charge before has to be the total charge after, okay? And everything is going to distribute that charge evenly to spread things out, okay? So let's do one more example. If I had, now these are the simplest examples. I'm sure that in physics classroom you'll find a few more challenging ones, but for the sake of simplicity, if I had two pith balls that are touching, and then I approach that with a similar sized object surface area that has 3 coulombs, as soon as I touch that, all that charge is going to distribute. Everything is in contact. And in the end, I would have, okay, this would be positive 1 coulomb, positive 1 coulomb. The pith balls would separate, okay, and then my charged object is going to be positive 1 coulombs, okay? And that's that principle of conservation of charge, okay, and distribution of charge. So everything wants to spread evenly as long as they have the same relative surface areas, and that charge is going to be distributed so that the charges are all repelling to the same amount on those materials, okay? Now, let's go on to the next stuff that we're going to be doing, okay? So we talked about what is a charge, how to calculate the total amount of charge, what is the principle of conservation of charge. Now, the next thing we're going to talk about is Coulomb's law, measuring the forces exerted by charges on each other, okay? So what Coulomb's law states is that the force experienced between 2 point charges at a specific point in space, is directly proportional to the product of their charges and inversely proportional to the square of the distance separating them. This is a true definition, and it looks a lot like our definition for gravity that Sir Isaac Newton created. That definition for gravity said that the force of gravity experienced between 2 point masses in space is directly proportional to the product of the masses and inversely proportional to the distance separating them. I hope you remember when we talked about that. That's the universal way of calculating the force between anything in the universe, all right? And this capital G is a constant, okay? It's a gravitational constant that would have been determined in a graph, and G is going to be 6.67 times 10 to the minus 11. That's my G, okay? So we worked through that, and something else that's important is, here, let's use a different color. Something else that's important is that R squared, and that's called the inverse square law, okay? So field forces, like I talked about in the last little video, any force that acts over a distance without contact obeys the inverse square law, where that force weakens by the square of the distance separating it, okay? And you can see in Coulomb's law, like I like this little comic here, it says that Coulomb copied Isaac Newton. Well, they both were studying field forces, and they have a similar relationship. They both obey the inverse square law, okay? So they look almost identical. All right, because they both are field forces, but just using different things. Isaac Newton's is mass, and Coulomb's law is charge, okay? So with Coulomb's law, the force is directly proportional to the charge of the first object times the charge of the second object divided by the distance in meters squared. And K is Coulomb's constant, okay? So with Coulomb's constant, K is 8.99 times 10 to the 9. Okay, so if I try to compare these, now it's not really fair to compare because mass and charge are completely different things, but you would think, you know, if they were relative, that the electrostatic force between charge is a lot greater than the gravitational force between mass. But you can't really think that because they're apples and oranges. You can't compare that. And what we have to remember is that our standard unit of charge is a coulomb, and a coulomb is a lot of particles. Okay, our standard unit of mass is a kilogram. That's not a lot of particles compared to a coulomb of charge, for example, okay? So something to just think about. You can't really compare that, but you can see that the structure of the formulas are relatively the same. So right now, we're just going to focus on this and applying it in some calculations, okay? So here's a diagram showing what Coulomb's law looks like. If I have a charge object here, you can see that that charge is probably larger than that charge. Okay, the force that is going to be acting between them is dependent on the distance between the center of those charges. That's the radius. Okay, so you take that charge times that charge divided by R squared times that Coulomb's constant, and you'd be able to calculate the electrostatic force that is equal and opposite on them. So the force experienced by that guy is going to be equal to the force experienced by that guy, and they're going to be equal and opposite, and they're going to be related to that. Okay, so let's do some practice. Before we do the practice problems, let's just talk about the experiment that we use to be able to determine Coulomb's law and the relationship. Okay, the experiment is the same one for gravity. I talked about this before when I just briefly mentioned in class how they measured that equation for universal gravitational law. What you'd do is you'd hang this torsion balance. Okay, there's a wire and a beam here with two masses. Let's imagine these are 1 kilogram masses. Okay, and they're metal balls. And in the middle, you have a mirror. Okay, and if I shine light at that mirror, it's going to reflect, and I can measure the angle of that reflection. Now, when I bring two charged objects up to this, and if I charge that with a known amount of charge, and I charge these objects with a known amount of charge, and I held them at a fixed distance, the whole thing is going to want to rotate. Okay, and there's a special formula to measure the force of tension in that wire as a function of by the angle it rotates. So they would be able to measure the force. So they're measuring forces measured, okay, by torsion. We don't need to know that for this class, but for next year you would. Okay, so the force is measured by torsion, how much that wire twists. Okay, and then the things that I can keep controlled, what I can change in the experiment is Q1 and Q2. I can change those, and I can also change the distance. Okay, so what they would have done is they would have kept some of these variables constant, and they would have changed them, and then they'd be able to work it out. How is it related? If I double the distance, triple the distance, what happens? And they're able to find out for distance, it's inversely squared is the proportionality. And for charge, when I change that, there's a direct proportionality. So after working through all those variables, they were able to come up with a graph that told them this formula, okay, or told Coulomb that formula. Okay, and it looks almost identical to the universal law of gravitation. All right, so let's do some calculations. What do I want you to do? What kind of math do I want you to do here? So how do we use that formula above to calculate the electrostatic force between charges of 1 times 10 to the minus 6 coulombs and 1.5 times 10 to the minus 6 coulombs when they are 5 times 10 to the 11 meters apart? That's a big distance. Okay, maybe is it? Yeah, maybe it's supposed to be 10 to the 1 meters apart. We'll figure that out in a second. All right, so let's take a look. So in order to calculate this, I would have to write out Coulomb's law first. All right, and then after I've written out Coulomb's law, I have to then plug in the numbers, okay? So, when I'm plugging in the numbers, I have 8.99 times 10 to the 9 times 1 times 10 to the minus 6 coulombs times 1.5 times 10 to the minus 6 coulombs. Okay, that's the second charge. Divided by 5. I think this is supposed to be times 10 to the 1, so I'm just going to get rid of that. It's times 10 to the 1. Let's imagine that, because for some reason my brain thinks it's definitely 5 meters apart. Okay, so if I did that calculation, I don't have a calculator on me, so I can't be able to fully describe this, but 8.99 times 10 to the 9 times those things, this should be around times 10 to the minus 12. Okay, divided by that, okay, maybe it's 0.5 meters is what it's supposed to be, minus 1. Yeah, and then that should give me the answer that I prepared on the page over there. So I apologize for my computer not writing that out properly. So the question should have read, calculate the electrostatic force between charges of that and that, okay, when they are 0.5 meters apart, okay? Next question, how far apart are 2-point charges of 2 times 10 to the minus 6 coulombs and 4 times 10 to the minus 6 coulombs if they produce an electrostatic force on each other of 5.6 times 10 to the minus 1 newtons? So again, all right, if you want to go ahead before I start, the answer is on the bottom here, and you can just pause it and try to figure it out yourself. But again, I would write the equation. Okay, and after writing the equation, I should rearrange the variables, okay? I'm not going to plug anything in until I rearrange the algebra. So how far apart, okay? The question is asking how far apart. So I want to isolate for r. So I'm going to move r squared is equal to k q1 q2 over f. Now stop for a second and try to figure out the algebra. Why did I do that? Okay, and then r is going to be equal to the square root of k q1 q2 over f. Okay, so all I would have to do now is I would have to plug in all these numbers into everything here. Now this is 8.99 times 10 to the 9, but I'd plug in that number here, plug in that number here, and plug in that number here, and that should give me the answer of 3.6 times 10 to the minus 1 meters. Okay, last question. Now this is one little bit more of a step up in difficulty, okay? So 2-point charged objects, okay, so if I have 2-point charged objects, they don't tell me the exact charge, so I'm going to call this Q1 and Q2. If they're separated by a distance, the force is going to be equal to 6.2 times 10 to the negative 2 newtons. And then, if I separate them by 3D, okay, the force then becomes what? Okay, that's what the question is asking. Now, this is a challenge. This is a challenge because they didn't give me the charges in this problem. They didn't give me anything else. But if you know, in both these equations, the charges stay constant. Okay, so what I'd have to do is a systems of equations. All right, and if I did the systems of equations, so I set up the first one. F is equal to K Q1 Q2 over D, okay, squared, all right? Then this one is F is equal to K Q1 Q2 over 3D squared, okay? What I can do is I can set up a relationship because I know, now here comes the challenging part. I'm just gonna show you some higher level thinking here. K, Q1, and Q2 are constant. K, Q1, and Q2 are constant. So what I can do is I can rearrange this equation so that one side will be the same in both equations, all right? So if I did F times D squared is equal to K, Q1, Q2, and on this side, sorry, this is the answer over here. I'm gonna move that answer a little lower. Okay, and on this side, if I did F times 9D squared, okay, I just expanded that out, is equal to K Q1 Q2, okay? You can see that I could substitute K Q1 Q2, so K Q1 Q2 is in both of these equations, so I can just substitute that in for K Q1 Q2. So then I'm left with F times D squared is equal to, that's a different F, okay? This is the new force, F prime, equals 9 times D squared, okay? Hope you are able to see that. And then I can cancel out the D squares, and I'll be left with F divided by 9 is equal to F prime. All right, so if I look at the original force was 6.2 times 10 to the minus 2. So the answer should be 6.2 times 10 to the minus 2 newtons divided by 9 is equal to 6.89 times 10 to the minus 3. All right, now this problem is definitely a 7-8 problem for us. So next year, this is a very standard and easy physics standard level problem, but for us right now in grade 10, this is the harder of the three. Okay, this is where you got to manipulate formulas and feel comfortable making your own relationships. Okay, so again, just to go over this, I had to create systems of equations in order to be able to solve by what factor does this force decrease compared to that force. Okay, so then after setting up those relationships, I could then use substitution to create that relationship, and then I moved things over. So the original force divided by 9 is equal to F prime, the diminished force, and then I was able to then calculate that. Okay, that's just one level of difficulty harder. Okay, so what I want to do now is I'm going to talk about the applications. So what applications do we have of electrostatic forces? Okay, so aside from just measuring electrostatic forces, there's many charged objects in your body. For example, ions and chemicals, and DNA is charged. So DNA actually uses electrostatic forces to build itself up. Okay, you learned that with Mr. Sickles last year, how DNA works. Okay, so a lot of biology works with electrostatic forces. You use them all the time. But what I'm talking about in terms of applications is tech. Okay, what kind of tech do we use for this? Okay, and this picture that I have over here is a spray nozzle that shoots paint. Paint is positively charged at a wall that we plugged in and made negatively charged. Okay, so if I just shot that paint in the room, all the paint particles are going to be attracted and they're going to accelerate to the wall. The wall will paint itself. That's pretty cool. You don't have to have anybody like painting the wall up and down, up and down. All you have to do is spray a room with that paint and the particles will be attracted to the wall and paint itself. That's probably one of the coolest applications. So when they'll do that, electrostatic painting, that would be for painting cars, like BMW does that. Okay, and it creates a very nice even coat. So painting metal beams or metal car frames are usually done in this way. You don't need a person. You just have to put the metal body in the room, charge it up, and then spray a bunch of those charged particles, okay? And likewise, photocopying machines also work the same way. The toner is charged, okay? And it'll be attracted to paper. Your paper is going to insert these charged particles where they want the toner to go, and the toner then sticks to the paper, okay? So those are just two applications, and I bet you can find more, all right? And that's what we're going to talk about next class.